we're going to talk about something very interesting. But before we get started, let me show you some of my analytics. Now, these are the real recorded COVID-19 cases across different countries in the world. And they are divided into different columns, as you can see here. But before we go with our analytics, let me first define what a leading digit of a number is. Leading digit of a number is simply the first digit of a number. For example, in 416, the leading digit is 4, and in say 83, the leading digit is 8. Now, to state the obvious, leading digit can vary from 1 to 9 because every number starts from either 1, 2, 3, all the way up to 9. Now let's get back to our data. First, we look under the total cases column and note down the leading digit of numbers in this column. And then we take the frequency of every digit that is appearing. For example, we take how many times 1 is appearing, how many times 2 is appearing, all the way up to 9. And this is the data that I got. Now just to get a clear picture, I plotted a bar graph corresponding to this data. We see that 1 is appearing maximum number of time and 9 is appearing least number of time. Now, we do similar thing to the recovered cases column and active cases column as well and plot the bar graph of the corresponding data. And the results are astonishing because even in those two columns, we get similar result. 1 is appearing maximum number of time and frequency of 9 again is minimum. We see this beautiful pattern in all these three graphs where the frequency of 1 is maximum and it gradually goes on decreasing and 9 has the minimum frequency. Now why do we see this? Why do we see this in the data where the rate of recovery, active and new cases is completely different in all the countries? Well, it's because all this data follow a certain law, a law named as the Benford law. Now let's get to the interesting part and define what Benford law is. Benford's law states that the probability that a leading digit is 1 is 30% and the probability goes on decreasing subsequently and 9 has the least probability. Now due to this gradual decrease in the probability, we see a curve in the graph. This is strange because if there are 9 leading digits, the probability of picking any digit at random should be equally likely, which is 1 by 9, approximately 11%. But that's what we see. We see that 1 appears 1/3 of the time, which is 30%. Now there's a formula which gives us the probability of each digit. The formula is probability of picking a number with a particular leading digit d is equal to log to the base 10 1 plus 1 by d. So for d equal to 1, we get 30%. The fun fact about this formula is that it works with log of all the bases. It doesn't necessarily has to be log to the base 10. This pattern was first observed by mathematician Simon Newcomb. When he was going through his logarithm books, he observed that the initial pages were more worn out and dirtier as compared to the pages at the end. So he concluded that statistics involving numbers starting with 1 were more frequently used as compared to other numbers. And later on, physicist Frank Benford proved this law, so the law was named after him. But this law is not seen in every distribution. The key constraint for this law to be followed is that the distribution should span to a large order of magnitude. For example, if we take distribution containing human height, we won't see this law being followed because usually human height is 1 point something meter and we don't see a 3 meter or a 4 meter tall human. But if we take distribution containing population of different countries, this law will work fine because that distribution contains magnitude varying from few thousand to a few billion. Now what's fascinating thing about this law is that this pattern is seen in distribution where we don't expect it to be seen. For example, this pattern is seen in distribution of stock prices, in length of rivers, in universal constants, in areas of country, and even in YouTube videos view count. We see this strange law being followed there as well. Now, this law has real world application as well. This law is actually used to detect banking and accounting related fraud. For example, if an employee or a company is faking its expenses and throwing in random numbers in its expense report, the expense report won't follow the Benford's law and the embezzlement will be detected. There is a general idea on why this law works, and the reason is because a number system starts with 1. Yes, the reason why this law works is because number 1 comes first, and because of the fact that a number system is of base 10. Let me give you a detailed explanation. In a number system, we start counting from 1. So 1 is a leading digit here. Now, the next instance where 1 is a leading digit is when we reach the number 10. So 1 has to traverse to 8 digit for it to be the leading digit again. 2 has to traverse to 17 digit for it to be the leading digit again. Similarly, 9 has to traverse to 80 digit for it to be the leading digit again. So we again see a pattern here where as we move forward, the numbers have to traverse more for them to be the leading digit. So 1 has to traverse through least numbers and 9 has to traverse through maximum numbers. And this pattern keeps on repeating itself as we move forward to 100, thousands and so on. By looking back at everything that we have seen in this video, we can conclude that in a sense, a number system is biased towards number 1. Hope you enjoyed the video and thank you for watching.